Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry, you did your part.
Hello everyone, and welcome to the third episode of the Organic Chemistry live stream, in which we talk about organic chemistry. For those of you who are watching live, first and foremost, I want to thank you sincerely for your patience and apologize profusely for my absence. As you may or may not know, I do my best to keep to my weekly streaming schedule, Sunday nights, 9 o'clock p.m. Eastern Time. However, on Sunday the 8th, I was sick. So I was sick for a couple of days, kind of lingering on. Not a horrible illness, but just annoying enough for me not to want to stream. And then last night I tried to go live, but my microphone wasn't working. It's like the universe just doesn't want me to go live. But here I am, live, 4 days overdue. So, all right, hope you all are doing well. I think tonight is going to be a pretty good show, but obviously you, the audience, are the judge of that. And so to that end, I'd like to say, please leave me your feedback. Your feedback is absolutely essential to the growth and improvement of this show, because if there's one thing I could use, it's some growth and improvement. Oh, man. The February and March weren't too bad, but April was a horrible month for my channel. And May, so far, it's not looking too good either. So, yeah, I could definitely use some support for sure. All right. So what we are going to do tonight is we are going to finish the job that we started the last stream, which was to review the general chemistry concepts that apply to organic chemistry, right? So that's what we're going to do. And we're going to go into pretty thorough detail, because that's one thing I like to do on this program, is I like to go into thorough detail. You see, my goal is not for you to simply pass your chemistry class. Instead, my goal is for you to whoop your chemistry class's ass, okay? So I want you to have a very, very thorough understanding of the chemistry so that you'll be able to crush your exams, get the grade that you want, or just learn more, know more about the world, improve your critical thinking skills. Because, I mean, just turn on the news, right? There's a severe lack of critical thinking in our society, so it's good, right? It's good to study chemistry because it kind of helps you think logically and critically. All right, so let's go ahead and start things off. So one thing that I did last week was I put out this question on my community page. I think that's something that I'd like to start doing like every week, like after every stream, just post a question that's sort of relevant to the stream that we just did. So this is the question of the week. It's asking for the hybridization and geometry around the central atom that is shown here in blue, right? So this is the nitrate ion. The nitrogen is the central atom that we're looking at. And I want to give some big congratulations to those who answered the question correctly. Their names are listed on the screen here. I'm not going to attempt to read them because chances are I'll pronounce at least one of those incorrectly. But to those of you who are shown here, thank you for answering the question correctly. So I guess we can sort of start things off by just taking a look at this question, which kind of just ties into a little bit of review from the last stream. So let's go to the whiteboard here real quick, where I already have this molecule up here on the board. So we're looking for the hybridization and molecular geometry, right? So remember, with hybridization and molecular geometry, to figure out what the hybridization is, you need to count the number of sigma bonds and lone pairs around the central atom. So let me write that down. I'm talking about sigma bonds and lone pairs of electrons around that central atom, right? So in the case of this nitrogen, how many sigma bonds and lone pairs? Well, it looks like there aren't any lone pairs, and it looks like there are 1, 2, 3 sigma bonds, not 4 sigma bonds, right? That double bond only counts as 1 sigma bond, because remember, a double bond is composed of 1 sigma bond and 1 pi bond, right? So if we have 3 sigma bonds, 0 lone pairs, that means we have 3 sigma bonds and lone pairs, right? And so if there are 3 then that corresponds to sp2 hybridization, right? Because if there are 3 sigma bonds in lone pairs, it's going to take 3 orbitals to accommodate all those electrons. sp2 is the hybridization that is associated with 3 orbitals. One s combines with 2 of the p orbitals to make 3 sp2 hybrids, right? And the approximate bond angle, the geometry around this, would be approximately 120 degrees. And we'd call this a trigonal planar geometry. So I'll go ahead and write that in real quick too. Trigonal planar. Right? If there were 4 bonding pairs and lone pairs, that would be sp3 hybridization with a tetrahedral geometry and an approximate angle of 109. And if there were 2 sigma bonds and lone pairs, that would result in sp hybridization with an approximate bond angle of 180 degrees, right? So it really just comes down to the number of sigma bonds and lone pairs around that central atom. A word of caution, right? Hybridization usually generally only applies to central atoms, right? Atoms that are bonded to at least 2 other atoms. It doesn't really apply to terminal atoms, atoms that are only bonded to one thing. Why? Because hybridization costs energy, right? Hybrid orbitals, they're kind of lopsided, right? They don't have as even of an energy distribution as s orbitals or p orbitals do, right? So because hybridization costs energy, the molecule sort of makes that difference in energy up by forming more bonds. So if you only have one bond, if you're a terminal atom, you tend not to hybridize, okay? So if you'd like more detail, I went into this in thorough detail in my last stream, which was part 1 of the general chemistry review for organic chemistry. So, all right, I think we can sort of move on here. I'm going to take you back to the PowerPoint. We're going to get into some new old content, so to speak. By the way, like I said before, I would love your feedback, so please feel free to shoot me a message in the chat if anything sounds confusing, or if you have any questions about anything at all, questions, comments, concerns, whatever, just type it in the chat. Just identify yourself. Let me know who you are. All right. So notice that in this structure here, in this Lewis-Kekulé structure for the nitrate ion, I've included some positive and negative signs. There's a positive sign, a plus sign on that on that nitrogen atom, and there are negative signs on the oxygen. So what's the deal with that? Why is there a plus here and a minus over here on these 2 oxygens? And the answer has everything to do with a concept called formal charge, and that's the first topic that we're going to talk about today. So I asked that question just a moment ago about the positive and negatives on that nitrate ion, but another question that I wanted to sort of pose to you guys to introduce the concept of formal charge is, why is NH4 plus, the ammonium ion, right? Why is that charged, but NH3, just plain old ammonia, is not charged? Okay, so what is it about the nitrogen gaining an extra hydrogen and having 4 hydrogens on it that makes it positively charged, right? Whereas when it has only 3 hydrogens on it, it's not charged at all. I really need some water. My voice is starting to crack. So, in other words, what I'm trying to figure out here is, what is the origin of the positive charge in that ammonium ion, right? So when a nitrogen has 4 hydrogens bonded to it, which atom in this molecule accounts for the positive charge? Now, to answer that question, we need to understand the concept of formal charge. So formal charge is a concept that is very, very important in organic chemistry. Very, very important that we know this, because it's going to keep popping up over and over and over and over again throughout our exploration into organic chemistry. So formal charge, what does it tell us? It tells us where on a molecule a charge is located, right? And there's a pretty simple formula for how to calculate formal charge, and that formula is shown down here in blue. So to get the formal charge of an atom within a Lewis-Kekulé structure, you simply take the number of valence electrons in the free atom, which you can easily find by identifying which group of the main group elements that element belongs to, and then subtracting from that the non-bonding electrons, the lone pairs, and half of the bonding electrons, right? So if you have let's say you have a single covalent bond is composed of 2 electrons. Formal charge basically treats that bond as though it's split down the middle. One of the electrons of that single bond belongs to one atom. The other electron in that single bond belongs to the other atom, right? So if we revisit, well, before we revisit the ammonium ion, let me just add this here. So one thing that's very, very important to understand about formal charge is that the sum of the formal charges within a molecule or within a polyatomic ion must be equal to the charge of the molecule or ion. Obviously, if it's just a molecule, it has no charge, which means the sum of the formal charges must be 0. And if it's a polyatomic ion, that means the sum of the formal charges must be equal to the charge of that polyatomic ion. And the convention in organic chemistry, when you're writing out a structural formula for a molecule or ion, is to show the location, sign, and magnitude of all non-zero formal charges, right? So let's go to the whiteboard once again. I want to revisit the ammonium ion. So let me take you guys to the whiteboard, and we will erase all of this junk. So I'm just going to draw what we had on the screen previously, where we had that nitrogen, where it was bonded to 4 hydrogens, right? And so what I want to do is I want to calculate the formal charge of every atom in this structure, starting with the nitrogen, right? So we know that formal charge is equal to the number of valence electrons in a free atom minus the non-bonding minus half of the bonding electrons, right? So for nitrogen, how many valence electrons are in a free atom of nitrogen? That would be 5, because nitrogen is in the 5th group of the main group elements within the periodic table, right? And we're going to subtract from that all of the non-bonding electrons. Notice that there are no non-bonding electrons. There's no lone pairs around that nitrogen there. And then we're going to subtract 1/2 of the bonding electrons, of which there are 2, 4, 6, 8, right? So it's 5 minus the quantity of 1/2 times 8, which is simply 5 minus 4, which is equal to plus 1, right? And so the formal charge of that nitrogen is plus 1. The convention is to show the location, sign, and magnitude of all non-zero formal charges, so we'll put that plus sign with an understood one right here next to that hydrogen, right? So let's figure out the formal charge of each hydrogen atom, right? Now, we don't have to do all 4 of these hydrogen atoms individually, right? Because they're all identical, right? Whatever we say about this hydrogen up here, we're also saying about the other 3 hydrogens because they're indistinguishable, right? So hydrogen, valence electrons in a free atom minus the number, or minus the non-bonding electrons minus half of the bonding electrons, right? So how many valence electrons are in a free hydrogen atom? That would be 1, because hydrogen is in the 1st group of the periodic table. And we're going to go subtract from that all of the non-bonding. Of course, there's no non-bonding electrons around that hydrogen. Half of the bonding electrons. There's 2 bonding electrons around that hydrogen. So half of 2 is 1. So 1 minus 1, which is equal to 0. So we have a formal charge of plus 1 for the nitrogen and 0 for the hydrogen. And just as we stated a moment ago, the sum of all those formal charges must be equal to the charge of the ion. So in the case of NH4+, that's true, right? Because if we add 4 zeros and a plus 1, we get plus 1, which of course is the charge of the ammonium ion, which remember has the formula NH4+. Okay, so we understand how to calculate formal charge. But the thing is that if you practice these molecules over and over and over again, you do all the practice problems that are in your textbook and everything, you'll start to get an intuitive sense of whether an atom is going to have a non-zero formal charge or a zero formal charge. You'll just notice the pattern. You'll instinctively see the number of bonding pairs and lone pairs around that atom, and you'll think to yourself, I think that should be charged, right? Because you will have seen it so many times, right? And so to demonstrate this, basically what I'm going to do is we're going to go back to the PowerPoint here, and I'm going to show you guys some common formal charges for a couple of different elements in the periodic table. We're going to look at carbon, nitrogen, and oxygen because those are among the most common elements within organic chemistry, right? So here's just a table or a chart that has some common formal charges of carbon, right? So we've seen in our general chemistry review that carbon forms 4 bonds usually, right? Each element of the main group elements forms a predictable number of bonds. In the case of carbon, that's 4, right? So by bonds, I just mean bonding pairs, right? So in all 4 of these cases over here on the left side of your screen, there's 4 bonding pairs, 0 lone pairs around that carbon, whether we have 4 single bonds, a double bond and 2 single bonds, 2 double bonds, or a single and a triple bond. In all 4 of those cases, there's 4 bonding pairs around that carbon, 0 lone pairs, and so consequently, the carbon in all 4 of those cases has a formal charge of 0, right? But what if the carbon had 3 bonds and no lone pairs? Well, that would result in a formal charge of +1 for that carbon atom, right? And such a chemical species actually has a name. It's called a carbocation. And we're going to look at carbocations in much more thorough detail later on because there are many organic reactions that proceed by mechanisms that include carbocation intermediates, right? Another common formal charge of oxygen is when you have a carbon atom with 3 bonding pairs and 1 lone pair. That will result in a formal charge of -1, and we call that type of chemical species a carbanion, right? Negatively charged ion, right? So those are just some common configurations of carbon with their associated formal charges. So let's move on and talk about oxygen, right? So oxygen, it's got 6 valence electrons in a free atom. Generally, on an uncharged atom, oxygen will form 2 bonds. It'll have 2 bonding pairs around it. So it could have either 1 double bond with those 2 lone pairs or 2 single bonds with those 2 lone pairs, as it does in a molecule of water, for instance. So in both of these cases, the formal charge of oxygen is 0. But there's a couple other possibilities as well, right? If you had a single bond and 3 lone pairs, which is pretty common for oxygen, that'll result in a formal charge of -1, right? So again, if you see a molecule where there's an oxygen atom and it's got 1 single bond and it's got 3 lone pairs, right? Again, if you practice this enough, you'll immediately understand, like, oh yeah, that oxygen should be negatively charged, right? Because you will have done it so many times. That's the level of understanding that I want to sort of help you get to with regard to formal charge, right? And there's a couple of other instances in which oxygen has a +1 formal charge. So, for instance, if you have a lone pair and 3 bonding pairs, right? Whether that's a lone pair and 3 single bonds or a lone pair and a single bond and a double bond, these are both pretty common for oxygen. Both of those cases, you'll have a formal charge of +1. Like this one up here, where you've got 1 lone pair and 3 bonding pairs, right? That is the configuration of oxygen that exists in the hydronium ion, H3O+, which is like really, really common when you start studying acids and bases and stuff like that. Hydronium ion, right? pH is based on the concentration of hydronium ion. Hopefully that rings a bell. Okay, there's oxygen. And then we're also going to talk about nitrogen. So what are some common configurations of nitrogen and their associated formal charges? Well, here's a few of them. So nitrogen generally likes to form 3 bonds. That's how nitrogen maintains neutrality, maintains no charges by forming 3 bonds, whether that's 3 single bonds, a single bond and a double bond, or a triple bond, right? In all 3 cases, we have a lone pair. In all 3 cases, the formal charge of nitrogen is 0, right? But there's a couple other possibilities as well. Nitrogen can have a +1 formal charge if it has 4 bonding pairs and no lone pairs, just like the example that we were looking at a moment ago with the ammonium ion, NH4+, that would apply to this particular structure or this configuration of nitrogen here, right? So again, the whole point of all of this is to show you things that you will see over and over and over again, and upon seeing them over and over and over again, you'll be able to immediately connect in your brain with what the formal charge should be without calculating formal charge directly using that formula, right? So it's important to have the formula in your back pocket if you're ever unsure, if you ever get stuck or whatever. But what I want to try to do is to develop that level of understanding where you really don't even need the formula because you have that experience of having seen it over and over and over again. All right, so that's formal charge. So the next very, very important topic that we're going to talk about is something called resonance. So I'm going to definitely take my time covering the concept of resonance because I believe that this is one of the most commonly misunderstood topics within general and organic chemistry. So to introduce the concept of resonance, I'd like you to consider the Lewis-Kekulé structure for the formate ion, which has the formula CHO2 minus, right? CHO2 minus. If you were to follow the step-by-step instructions for drawing Lewis dot structures, and you would apply that to the formate ion, you would end up with a structure that perhaps looks like this, right? So we've got a carbon atom in the middle, right? It's bonded to a hydrogen. It's bonded to two oxygens. One of those oxygens is a double bond, and that oxygen has two lone pairs and a 0 formal charge. The other oxygen is singly bonded to that carbon. The carbon and the oxygen are connected by a single bond, and that oxygen has 3 lone pairs and a formal charge of -1, right? So this is one possible way that you can draw the formate ion, right? But there's another way that you can draw the formate ion. You could draw it like this, right? So I've got these two sort of structures here, right? Two different ways of drawing the same thing, right? So in the structure on the left, the oxygen on top is the one that's pi bonded, that's double bonded, and has no charge, while the oxygen on the bottom is the one that's singly bonded and has the negative charge. In the structure over here on the right, it's the opposite. The top oxygen is the one with the single bond and the charge, and the bottom oxygen is the one with the double bond and no charge, right? And so how do we choose which oxygen is which? How do we choose which one gets the double bond and no charge and which one gets the single bond and the negative charge? What do you guys think? Because this structure, as it's written, implies that the pi electrons that form this double bond here, right? Because remember, a double bond is a sigma bond and a pi bond, right? This structure implies that the pi electrons of the double bond are confined to the space between those two pi bonded atoms, right? So in other words, we would expect, if we were to study this molecule, right, we would expect there to be two different kinds of oxygen in this molecule, right? We would expect the bond length to be different between the carbon and this oxygen and the carbon and this oxygen. I just realized my mouse cursor is not visible. So again, if we were to accept one of these structures as the truth, right, we would expect two different oxygens and two different bond lengths, right? Because remember, double bonds are shorter and stronger than single bonds, right? Now, experimentally, chemists have sort of looked at this, and chemists have found that both carbon-oxygen bond lengths are the same. They are 127 picometers. So just to put that into perspective, a typical carbon-oxygen single bond has a bond length of roughly 135 picometers. A typical carbon-oxygen double bond has a bond length of 120 picometers, right? So 127, that's kind of like in the middle between a typical carbon-oxygen single bond and a typical carbon-oxygen double bond, right? There's only one type of oxygen in this molecule, even though, according to our structures, it looks like there's two types of oxygen, one that's doubly bonded and one that has a negative charge. So what's going on? How do we explain this? How do we resolve this? And the truth of the matter is that neither one of these pictures tells the whole story. So what we're looking at here is a deficiency of how we draw Lewis-Kekulé structures, right? We need a better way to draw what's really going on here, right? The truth is that both of these bonds, or neither of these bonds between carbon and oxygen, are a full single bond or a full double bond. They both have characteristics of both. They have characteristics of both single bonds and double bonds. So what's going on, right? And the answer is something called resonance delocalization. right? So what's really going on is that the pi electrons and the negative charge in formate ion are actually spread out over a wider region within the molecule, right? So the pi electrons in that double bond are not confined to the two atoms. They are spread out over a larger network within the molecule, right? And one way to represent that is by using something called resonance structures, which are also called resonance forms, right? And so the two resonance forms of the formate ion are shown up here. And notice that they are separated by a single arrow with two heads on it, right? It's not an arrow with one head on it, which indicates a chemical reaction. It's not those two half-headed equilibrium arrows that point in opposite directions, which would indicate a reaction under dynamic equilibrium. No, it's a single double-headed arrow, right? So these are the two resonance forms, right? And a more accurate picture of the formate ion is shown here, right? And this is called the resonance hybrid. Again, it's more accurate, but it's not drawn as much as the two individual resonance forms, right? And so you see how in this hybrid drawing, you kind of have like the double bond sort of shown as like a dotted line that connects to both oxygens. The negative charge is sort of shown like in the middle, right? So what these structures are intended to represent is that the pi electrons and the negative charge are spread out over all three of those atoms, the oxygens and the carbon, right? And so at the molecular level, why does that happen? So let's take a look at the orbitals, right? Because if you want to know more about the bonding behavior, which would include resonance, at some point you have to take a look at the orbitals, right? And so this is sort of, I have a model here. So this is just a little molecular model of the formate ion, right? So what I'm looking at is I'm looking at that 3-atom network of the carbon and the two oxygens. So this is kind of what I'm looking at right here, right? So imagine that image that's shown on the left-hand side of your screen is sort of like what I'm looking at right here, where the hydrogen is sort of hidden back here. I'm looking at these 3 atoms, right? So all of these 3 atoms, they have p orbitals, right? The carbon, on account of having 3 sigma bonds and lone pairs, or 3 sigma bonds and 0 lone pairs, is sp2 hybridized, right? sp2 hybridization. That means the s orbital combines with 2 of the p orbitals to make 3 sp2 hybrids. The third p orbital, because remember there are 3 p orbitals total, right? The third p orbital that didn't get involved in hybridization, it's still hanging out. It's still unhybridized, right? So the carbon has a p orbital, right? And each of the oxygens also has a p orbital as well. And whenever you have 3 or more atoms, 3 or more contiguous atoms with parallel p orbitals, those parallel p orbitals actually serve as like a conduit. They serve as like a channel through which the electrons can be spread out or delocalized among all of the atoms in that contiguous network of atoms, right? So whenever you have those parallel p orbitals, what happens is that the pi electrons, the electrons that participate in the pi bond, and the negative charge is spread out. It's delocalized across this 3-atom network. So that's what we call resonance delocalization. And if we look at the two resonance forms, again, the two resonance forms seems to imply that we have like an equilibrium where one of the structures exists for a short period of time and then it converts back to the other structure and it goes back and forth. No, that is not what's happening at all. These two structures are showing you the extremes, right? These two structures, what we do is we look at these two structures and then we sort of blend them together in our mind, right? We're using two structures to show that the pi electrons and the negative charge are spread out over a larger area within this molecule, right? And so, keeping that in mind, let's talk a little bit more about some principles to keep in mind with regard to resonance. I can either jump into this, or we can look at another molecule, another Lewis dot structure that can be represented by multiple resonance forms, whatever you guys want. The chat is whisper quiet tonight. I don't know why anybody's not chatting. Usually I get at least a couple of messages, but yeah, what do you guys think? Should we talk more about the principles, or should we maybe go to the whiteboard and look at another molecule that can be represented by 2 or more resonance forms? I got a message from Rahaf, says, hey, just joined. Hello and welcome. That goes to everybody who's watching. Welcome. Good to have you in here. All right, so yeah, I guess I'll just rely on your guys' feedback. Leave a comment or type in the chat. Let me know if you believe that you have a good understanding of resonance by the end of this stream. And then maybe next week we can talk a little bit more about it, because I really, really want to spend as much time as it takes. I want to do whatever it takes to make sure that we all have a good understanding of resonance, because it is, like I said, it's a pretty commonly misunderstood topic. It's also a topic that's pretty hard to teach, if I'm just being honest. So, all right, so let's continue. So here's a couple of principles to keep in mind with regard to resonance. So the first one is the following. Resonance delocalization of electrons lowers the energy of the molecule or ion, right? Because whenever you have energy dispersed over a larger volume or a larger area, you have a lower potential energy. Lower energy means more stability, right? And so if we look at for instance, the formate ion, which we just saw, and again, there's only one formate ion, but we just use these 2 resonance forms to show the spreading out of the pi electrons and the negative charge, right? The formate ion is more stable than this species over here. This is formic acid. So this is basically like the formate ion that's picked up a hydrogen atom, that's picked up a proton, right? And notice that formic acid over here cannot be represented by 2 or more resonance forms. There's no resonance forms. This doesn't participate in resonance, right? There's no resonance delocalization of pi electrons going on in this molecule. Why not? Well, because we don't have 3 contiguous atoms with parallel p orbitals, right? This oxygen up here, it has a p orbital. This carbon, since it's sp2 hybridized, it also has a p orbital, but this oxygen doesn't have a free p orbital. It's sp3 hybridized. It's got 2 lone pairs and 2 sigma bonds. So all the p orbitals in this oxygen down here are involved in hybridization. There's no pure p orbital that can line up in that parallel overlap with the p orbitals of those other 2 atoms to give you resonance delocalization. Doesn't work, right? And so it's kind of interesting that by losing a hydrogen, formic acid, when it converts to formate ion, becomes significantly more stable on account of resonance delocalization, right? And the result of that is that formic acid tends to be a fairly strong acid, right? It really, really wants to get rid of that hydrogen atom so it can enjoy the low potential energy associated with resonance delocalization. That sound okay so far? I hope so, because we're moving on. All right, so another thing to keep in mind when you're looking at resonance structures, resonance forms, and this and that, is that resonance forms must be legitimate Lewis-Kekulé structural formulas, right? In other words, you can't really violate the octet rule. You can't have like a carbon with 5 bonds on it, or like an oxygen with 7 lone pairs or some shit. You can't have that, right? They have to be legitimate Lewis structures. You follow those step-by-step instructions that we outlined in the last live stream. Yeah, you can't violate any of the rules that we've learned so far. And another thing that's really, really important to understand is that resonance forms differ only in the position of pi electrons and non-bonding electrons, or lone pairs, right? Which means you cannot move the atoms and you cannot move the sigma bonds, right? So when you're looking at a molecule, right, and you want to know, or let's say you know that there's another resonance form of that molecule, you want to figure out what it is. You imagine that those atoms are like bolted into place. The sigma bonds are like bolted into the page and you can't move them. All you can move are the pi electrons, which again apply to double and triple covalent bonds, and the non-bonding electrons, the lone pairs, right? Another thing that's really, really important to keep in mind with resonance is that the real molecule or ion that can be represented by multiple resonance forms is lower in energy than any of the fictitious resonance forms in which the electrons are localized. So in other words, the resonance hybrid of if we return to our example of the formate ion, right, that resonance hybrid that we use two resonance forms to represent is more stable than either of these two structures that depict the pi electrons as if they are confined to the region between the two atoms, right? So that's kind of important to understand. And then the next thing is that resonance forms don't necessarily have to be equivalent with one another, but oftentimes they are. In the case of formate ion, the resonance forms are equivalent, right? So let me blow myself up a little bit here, right? So if we're looking at the formate ion, right, let's say that this is one resonance form of the formate ion, right? If we turn it around like that, we get something that looks like the other resonance form of the formate ion, right? So that's an example of equivalent resonance forms. But let's look at an ion which is represented by resonance forms that are not equivalent. So this ion right here, CH2. Oh, look, I just got a subscriber. Thank you, Stan, for subscribing. Really, really appreciate it. So if we look at this ion over here, the CH2CHO minus, that's called the enolate ion, right? Its resonance forms are shown down here. And notice that these resonance forms are not equivalent. One resonance form has a double bond between two carbons. The other resonance form has a double bond between a carbon and an oxygen. They are legitimate Lewis structural formulas. They do differ only in the position of pi and non-bonding electrons, but unlike the resonance forms of formate ion, the resonance forms of the enolate ion down here are not equivalent. And just to make sure that we understand what we're looking at here, so the resonance form of the enolate ion that's on the left side, that sort of looks like this, right? Where you have the carbon atom, two carbon atoms bonded together by a double covalent bond, right? And then the other resonance form of the enolate ion looks kind of like this, right? I'll try to flip it the correct way, where you have the double bond to the oxygen and the two carbons are joined together by a single bond. So let me see if I can sort of blow myself up again and show the two non-equivalent resonance forms of the enolate ion, right? You got this one over here on your left with the double bond between the carbons. You got this one over here on the right with the double bond between the carbon and the oxygen, right? But again, they are resonance forms because they're legitimate Lewis structures and they differ only in the position of pi and non-bonding electrons. Everybody with me so far? All right, and then the last thing, I think this is the last thing that's important to understand about resonance forms is that contiguous atoms over which electrons are delocalized are described as conjugated. So conjugated is the term that we would say these atoms are conjugated, or another way to say it would be, this molecule or this ion is conjugated across X number of atoms, right? So in the case of the formate ion, right, we would say that formate ion is conjugated over this 3-atom network that includes the carbon and both oxygens. And I've highlighted the conjugated system, the 3 atoms that are conjugated, right? And then over here in the enolate ion, right, it's these 3 atoms that are highlighted that are said to be conjugated, right? So it's important that we understand that word. A lot of jargon in organic chemistry, so we have to make sure we understand it, we can digest it, so we can do a good job understanding the material. All right, so there's resonance for you. Again, this is kind of a hard one to teach, so if you're not satisfied with your understanding of resonance at the end of watching this video, or if you think we need more practice or whatever, right? If it's still confusing to you, let me know. Leave me a comment, because chances are, if you're confused about it, other people are probably confused about it as well. So let me know. I'm happy to expand on this topic even more, because it will definitely keep coming back over and over and over again as we continue in our exploration of organic chemistry. All right, so at this point, what we're going to do is we're going to switch gears, and we're going to talk about something else that's really important in the context of organic chemistry, and it's called electronegativity, which is something that you've probably seen before in your general chemistry class, right? So electronegativity, which is a property of each individual element in the periodic table, is the tendency of an atom to pull electrons to itself within a chemical bond, right? And you may remember from when you were studying periodic trends that electronegativity increases up and to the right in the periodic table. So electronegativity increases as you go up a group of the periodic table. Electronegativity increases going from left to right across a period of the periodic table. And if you want a more thorough explanation on this, look no further than my video. It's called What is Electronegativity? I discuss why the electronegativity trend is the way it is, and it explains everything in very good detail. So that's electronegativity. And you probably also remember from general chemistry, this is just a visual representation, right? Electronegativity increases going up and going to the right in the periodic table. So the highest rightmost elements in the periodic table are the ones that have the highest electronegativities, like fluorine. Fluorine is the most electronegative element, and this and that. And you probably also remember from when you were taking general chemistry that the type of bond, ionic or covalent or polar covalent, that forms between two atoms is determined by the difference in electronegativity, which we call delta En, right? So if there's a very, very large difference in electronegativity between two elements, as there is between, let's say, a metal and a non-metal, then that results in an ionic bond, right, in which you have the complete transfer of one or more electrons from usually a metal to a non-metal, right? So again, large difference in electronegativity results in ionic bonding. And if you have a very, very small or a zero difference in electronegativity, that results in a non-polar covalent bond. It's also called a pure covalent bond. You may know it by that name, right? So any diatomic element like H2 or Cl2, where you have two identical atoms bonded together, because those two identical atoms have identical electronegativities, that results in a non-polar covalent bond, a completely equal sharing of electrons between the two bonded atoms. And if you have a moderate, not too high, but also not negligibly small difference in electronegativity, that results in what we call a polar covalent bond, which means the electron pairs are shared unequally between the atoms. And the reason why this is so important is because the polarity of chemical bonds and the polarity of molecules plays a really big role in both the physical and chemical properties of the compounds that we're going to study in organic chemistry. So organic chemistry, usually we don't consider ionic bonding. There's not a whole lot of ionic bonding that occurs in organic chemistry. Organic chemistry primarily deals with polar and nonpolar covalent bonds. So we'll sort of keep that in mind. All right, now the next thing, and this is the last thing that I wanted to talk about before we're all done for the night, is some acid-base stuff, right? So you probably remember acid-base from general chemistry, so we're going to bring our knowledge up to speed on that, sort of give our refresh our memory on this. So remember, there's a couple of different definitions of acids and bases, and I think the one with which we're most familiar, the one that we use mostly in general chemistry, is the Bronsted-Lowry definition. And under the Bronsted-Lowry definition of acids and bases, an acid is a substance that donates an H+ ion or a proton in the event of an acid-base reaction, while a base accepts a proton from an acid in the event of an acid-base reaction. So if we look at, this is a sort of a detailed drawing of an acid-base reaction, right? So you've got your Bronsted-Lowry acid, which is shown up here as HA. A isn't a real chemical symbol. I'm just using A to represent the rest of the molecule in that acid, whatever that acid has to be, right? So this HA is like a general formula for my Bronsted-Lowry acid, right? And then my Bronsted-Lowry base I'm representing with the letter B, which includes a lone pair. All bases will include a lone pair. That'll always be true, right? So let's look at sort of how this works, how this Bronsted-Lowry acid-base reaction works, right? So what happens is that the lone pair of electrons on your base sort of gets connected to the hydrogen atom that's in your Bronsted-Lowry acid, right? So the lone pair forms a bond with the hydrogen, and then the pair of electrons that represents the single covalent bond between the hydrogen and the rest of the acid migrates over to the rest of the acid to result in the products here, which are BH+. That's the conjugate acid of the base. That is the base upon gaining an H+ from the acid. And over here, this A- species, that's the conjugate base of HA, which has a negative charge as a result of picking up an extra electron, because it picked up both of the electrons that used to be in that bond with the hydrogen atom, right? And notice the convention here showing this reaction. We're using curved arrows that show the direction of electron flow, right? So the tail of that arrow begins somewhere where it's an electron-rich environment, like a lone pair, right? And the head of that arrow is pointing to a place where that pair of electrons sort of attacks, right? To somewhere that is electron poor, right? So we're definitely going to get some more practice using curved arrows to show the direction of electron flow when we do organic reaction mechanisms and things like that. A lot of interesting stuff over the horizon. I just have to stay healthy and not have my mic break on me so I can keep doing my live streams. But anyway, all right. So that's the Bronsted-Lowry definitions of acids and bases. But there's another very, very important definition of acids and bases that you may have touched on a little bit in your general chemistry class, and that's called the Lewis definition of acids and bases. So this is something that's really, really big, really, really important in organic chemistry. Not so much in general chemistry, but in organic chemistry, the Lewis definition of acids and bases is very, very important. So it's important that we understand it, right? So under the Lewis definition, an acid accepts an electron pair from a base to form a bond. And a base donates an electron pair to an acid to form a bond, right? So it's different from the Bronsted-Lowry definition. Bronsted-Lowry, an acid is a proton donor, a base is a proton acceptor. In the Lewis definition, a base is an electron pair donor and an acid is an electron pair acceptor, right? So if we look at a detailed sort of mechanism, so to speak, for a Lewis acid-base reaction, right? You got your Lewis base here, shown as the letter B with a lone pair, right? And that lone pair forms a bond between the base and the Lewis acid to form something that we call a Lewis acid-base adduct, okay? So notice that the Lewis definition doesn't really do much with bases. It doesn't really expand the definition of bases, right? Because a base has like the lone pair in both cases, in the Bronsted-Lowry case and in the Lewis case. But under the Lewis definition, we now have a lot more possibilities on what can be considered an acid, right? Because in the Bronsted-Lowry definition, an acid needed to have a hydrogen. In the Lewis definition, an acid doesn't necessarily need to have a hydrogen. It just has to have a region of space that is electron poor that can sort of be attacked by a lone pair of electrons, like an empty orbital or something like that. And again, we're going to expand on this in much more detail later on. But just as in the last example, we're using curved arrows to show the direction of electron flow, right? And I'm sort of trying to color code these so that we can keep track, right? That lone pair that used to just belong to the Lewis base on the product side has now been converted to a single bond between what used to be the base and what used to be the acid to form the acid-base adduct. All right. So, okay, I think that is just about going to do it. Sorry about that. I'm kind of all over the place with my scenes here on my streaming software. But yeah, that's going to just about do it for us tonight. Thank you guys so much for being here. Not a lot of participation tonight. A little disappointed to see only one message in the chat throughout this entire 50 minutes or so that I've been streaming. But hey, it's all good. Maybe that just means everybody's listening. I don't know. But again, thank you very much. If you would like to support the stream, your support would be very welcome. Like I said before, I had a very, very poor month of April. May is not looking so great either. So what are some ways that you can support me? Well, you can leave a like on the video. That helps just a little bit with discovery. You can share the video with people who might be interested, right? So let's say you know somebody who's going to be taking organic chemistry soon over the summer or next fall or something, right? Or not even organic, but general, just any chemistry, right? If you know somebody who might be interested in chemistry for whatever reason, please send them a link to my channel. That would be great. Also, you can support the stream via Streamlabs. There's a link down low in the description. If you want a molecular model kit, you can build molecules like these. I have an affiliate link down below, so you can get yourself one. They're very, very affordable and awesome, fun to play with. And yeah, so there's a couple of ways to support the stream. You can also super chat. Of course, that option has been available for a very, very long time. So to those of you who are considering supporting the show, thank you very much. And I will see you in the next episode of the Organic Chemistry. Thank you, and have a great evening. Take care.